testing. Can you hear me?
Yep.
All right. So yeah, my talk is about pretty much the only thing that I do in Zig, which is IO and concurrency. So here's a little intro about me in particular. I go by Protty online. Real name is King Butcher. If you want to find me in like an actual professional setting. Right now, I am currently a co-founder of Tiger Beetle, which is a database, or is a company that writes a database in Zig for originally financial transactions, but now we're like scaling out to even more broader use cases. Also with Tiger Beetle, I am part of the Zig core team. I was working on a IO and concurrency project before called Zap, and then Andrew took notice and then kind of like snowballed from there into Zig core team. Now I can contribute to some IO and concurrency stuff on the standard library or do other parts, but the concurrency is where my focus is at. I also do blogs and drawings on some blogging sites, and you can find some of my drawings on either Discord or the Twitter.
More volume and
Okay.
more precision with the microphone.
All right.
Recognize me. Yeah.
It's gonna be just like home.
Sorry.
So the first thing that you probably can notice about IO concurrency is like what do you actually use it for? So one of the first things that comes to mind is like making a web server, because that's the most marketable thing for a language. Like everyone knows that tech and power benchmarks is false, but we still use it as a good bragging rights system. It's also a good place to test out low-level design decisions, because a web server isn't just you send request in, get request out. You also have to do scheduling for efficient request dispatch, some optimizations for parsing, some optimizations for how IO is like submitted in batch if you can, stuff like that. So it's actually a pretty interesting problem in general. So the goal of this web server in particular is to support at least 10,000 concurrent clients and at low latencies. That last part is actually pretty important. I guess you could try, like, if you were to do this yourself without having any knowledge of like how to write efficient web servers, you'd probably just spawn a thread per socket. And so that works, and it's actually recommended, but the issue is that it doesn't scale. So when you have more concurrency than the scheduler can handle, it starts having to oversubscribe the threads to all the cores. And so what this could mean is either some threads hog up the cores so much that other threads that still need to do IO don't get scheduled. And so in an IO setting, latency is actually more important than throughput. So current Linux scheduler, for example, because the Linux scheduler is probably what you're going to be running the web server on, it optimizes for throughput. So if you have, let's say, 1,000 threads, probably like 20 or 200 of them will actually be running most of the time. The other ones will get preempted by the 20 or 200. And so the tail latencies of your server is going to be really bad. So it can be like upwards of 1 second for one request to process on one of the unlucky threads. And so that's an issue for the latency side. And so one way we can solve that is by introducing non-blocking network IO. So with the socket or thread per socket model, each thread has only one socket that it can service, because when it does IO on it, it has to block the entire thread. And so you can get past that by using a scheme where instead of blocking the thread with one socket operation, you can have multiple socket operations on a single thread. And so you don't have to rely on the OS's thread scheduler for concurrency. And so you can optimize latency yourself. There's two types of ways for how to model non-blocking IO, and it really depends on what your OS gives you. The one that you're probably familiar with, if you know about POSIX, is the reactive and readiness approach. So basically, this is where you try to do IO, and the IO will tell you whether you could or could not do it, and then you can use an external system to tell you when you can retry. So this is convenient because it builds on top of existing POSIX systems where you already have the IO operation in front of you, or you already do it as first, And so this doesn't have to modify POSIX at all. It just modifies what the POSIX functions return. So you don't have to change APIs. So like read, write, you can still use those for files and sockets. All it does is just make read and write just return a different opcode that you can now handle in an async setting. The other version of that, which I'll get to why that's better, because it is better. The other version is completion based. So this is when you start an operation and then you have the system tell you when it's done, instead of having to retry it or maybe wait for you to retry it later. I'll go over the pros and cons for both of them in a second. But basically, these are both two systems of ways to handle multiple I/O on the same thread. And then that allows you to not have to use multiple threads and rely on the Linux scheduler for I/O concurrency in particular. But non-blocking I/O can actually be slower than blocking I/O, which is something that people don't really like to talk about. Because everyone's pushing for non-blocking I/O. Like they've seen Apache, and then they see Node destroy it, and then everyone thinks non-blocking I/O is the future. Technically, it is, but there are some reasons where it isn't. I'll go over it in a bit once we go over the pros and cons for this. So this is probably the first version of non-blocking I/O that you'll be touching if you ever try to get into the sphere of writing high-scale servers. On Linux, you have one popular syscall, which is epoll. And on BSD, you have KQ. They basically do the same thing. They just let you pull for sockets that I'll explain in a bit. So these are both readiness or reactive-based approaches. So basically, you have all the POSIX syscalls as before, then you try the I/O, it reports not ready, and then these two systems can tell you when to retry it again. So yeah, POSIX I/O can return E again, or E would block. They're basically the same value. I don't know why they both exist. Probably some POSIX specs thing. And then this part is optional, but you'd register the file descriptor for when you want to get a notification. There's ways to avoid this, and avoiding it is actually the most efficient thing to do, because having to re-register the syscall re-register the file descriptor every time you get an E again is actually pretty not performant. But yeah, the APIs just give you a way to pull for readiness or pull for when you want to retry on multiple operations. The issue with this is that there can be multiple syscalls involved in doing just one read. So you start off with a read, right? And then it gives you E again, you register it optionally, and then you pull for it to be ready, and then you retry the read again. So like this is about 3 to 4 syscalls for something that would normally be one syscall in a blocking I/O approach. So like if you have like maybe low concurrency levels, maybe like 5 or 6 threads just doing blocking I/O, that would actually be faster than doing the non-blocking I/O approach, because you're just doing less syscalls overall, and you're not oversubscribing the scheduler, so it doesn't matter what the latency spikes would be, because there wouldn't be any since it's not oversubscribed. So Linux and epoll and KQ are reactive, and they have this, I guess you would say, a con of their API design, which is resolved by Windows for whatever weird reason. So one of the things Windows does almost really right, is kind of its I/O APIs. So it's proactive and completion based, which also means that read and write take an extra argument called an overlap. And this overlap is sort of a representation of your asynchronous request. And so you try to read and write, and then it either completes immediately, which is also the case for POSIX, or it tells you it'll complete later on. But the thing with IOCP versus epoll is that when you pull the results, it doesn't tell you what to retry, it just tells you what the values were, so you don't have to retry at all. So this completely avoids the second syscall. You still have 2 syscalls for the start operation. It's going to tell you when it's done, and then you pull, and then it'll tell you the results. But it's still better than 3 syscalls for in operation, at least on like Linux or any Unix-based system. But there's one last inefficiency that Windows still has, which is that you can't do multiple I/O operations in the same syscall. Like read and write still have to do separate syscalls for that, for IOCP to function. Technically, I was gonna say technically that's not true because you can override it with some Windows AFD internal stuff, but I don't want to advocate for that because I've seen people mess it up so many times. So yeah, you have your server, you have it doing web request. You might want to make it useful by actually sending files over the network, like where else you would use a server for. So you want to do non-blocking file I/O because if you already have non-blocking network I/O, if one of your files blocks, then that kind of defeats the whole purpose of it. So you go to implement non-blocking file I/O, you look up online, you try something out, and it just doesn't work for whatever reason. There's some reasons that I do know of, and then some reasons I just do not know of, but basically file systems in the kernel, in multiple kernels, are just not structured for asynchronous I/O, or they have pitfalls that make asynchronous I/O become synchronous in some form or another. So like take on epoll and KQ. Basically, file or disk FDs, it just always return ready to read or ready to write. So you can't actually use it to efficiently poll for when to retry. On Windows, even though it has an I/O or asynchronous I/O for files, that API can just randomly block for whatever reason. This is actually documented by them. I always have the link ready for people who come to say to implement file I/O in the standard library for whatever reason. It can block for if the file is compressed, if it's encrypted, if the Windows page cache suddenly decides that your file isn't in the cache and has to refetch it, or any other random driver details that it has. It does not block for basically the equivalent of direct access. So you can open your file with unbuffered mode, so it doesn't go through the page cache. You can open it with a, I forgot the exact flag, but it's similar to ODirect on Linux, where it goes directly to the disk. That still blocks for the disk access, but it doesn't block for the other weird reasons that it blocks on Windows. Linux also has this thing called AIO, which people use and then don't use anymore, and it has an option to do non-blocking I/O, but that can also still randomly block. Linus has multiple rants online for why it shouldn't exist, and there's a good reason for that. But basically, all you're left with is if you can't do non-blocking I/O in the kernel, you basically have to provide such an API in user space. And the way people do that is by just using the thread pool. Put the file I/O on a thread pool, let it do its thing and block there, return back to the normal non-blocking I/O later. An issue with this is that you're going to a thread and back. So that can be overhead. You can amortize this overhead by making a really good thread pool, which I have a blog post on. But that doesn't, it still has the overhead for at least one of the requests going to and one of the last requests going back. And this can actually add up. So like in libuv, this is a practical example. So it has a function called uvqwork. libuv has a specific thread pool that's designed for blocking operations. So it uses this for file I/O, it uses this for DNS resolution, or any operation that would normally block the thread that it can't control on its own. Tokyo, which is a Rust framework, also does this. It has a separate thread pool just to run blocking I/O functions. This is configured separately from the main thread pool that it uses for non-blocking stuff. And even Golang does this to some extent, but it does it actually pretty interestingly. So Go has a background thread called sysmon, and this regularly monitors all the running Go routines in the system. And so if it sees one of them blocking on a syscall, it will just move its scheduler resources to another thread. So it's basically just spawning a new thread just automatically instead of explicitly with the other two. But it's still using the thread pool for file I/O. And this is what IOU ring was meant to solve. and why Gens Expo saved Linux. So IO-ring is a proactive and completion-based I/O. So it's similar to Windows. You start an operation and it'll tell you when it completes with the result. So it's efficient on that aspect. It also uses a ring buffer between user and kernel space. So this means that, yeah, I put some little small animations here. I don't know if you can see it. But this means that to poll for I/O, you don't have to do a syscall. Since it's just a ring buffer, you can just check the memory. So you can poll for I/O without a syscall. So that removes the minimum of 2 syscalls that Windows had before, down to 1. And that you can submit a batch of I/O since it's a ring buffer and it's a size larger than 1. So you can submit multiple I/O, and that resolves the other issue that Windows has. So how it works is that there's a submission ring buffer of basically structs that define syscalls, and then there's a completion buffer of the outputs of that syscall. So IOU ring is just a method to schedule a bunch of syscalls to the OS, do one syscall, and then get all the results back. Well, I think I clicked the wrong button. Okay. So yeah, the method to schedule this, the syscalls and the structs is called enter. This both submits and waits for completions, both at the same time. So Gens was really smart about this API decision. And so you don't have to do 2 syscalls like Windows, nor do you have to do 2 syscalls like Linux. You can just submit and wait for the completions at the same time. So having 1 syscall means that it can also do some other optimizations. So like when you submit them, it can choose to complete the file I/O in line, since the kernel is the kernel, and so it knows if a file I/O will block or not. So it can just complete it directly in line when you do the enter, or it just defaults to a kernel thread pool, because file I/O still isn't asynchronous in the kernel. It just uses its own thread pool, which is still better than a user space thread pool because it's more familiar with it, and it's the kernel and can do more stuff with it. Let's bring it back to Zig. So we know that IOU ring is pretty efficient at scheduling I/O. So what if we just made something similar to IOU ring that can get the benefits from it, but in a standard library fashion where it's supported by all platforms? I mean, it sounds like a good idea. One of the issues with IOU ring's design is the ring buffer itself. So this would be efficient for the use case of IOU ring, but when it comes to adapting this to other operating systems, it kind of falls flat in a few areas. So one of the areas that it falls flat on is you can have more in-flight operations than the ring buffer size. So let's say your ring buffer size is like 30, and you submit 30 operations, and you want to submit another. Should it have to allocate to submit the other one while the 30 are in flight? Should it have to block you from submitting until the 30 complete? Stuff like that. So you have basically implicit allocation that normally the kernel deals with, but now you have to deal with in user space, and the Zig community really doesn't like implicit allocation, so that's kind of against some of the goals. You also can't do the inline enter thing, so if you mimic IOU ring's API and have enter, when you do enter, it has it has the decision to do some of the I/O inline. That's not efficient in user space because you're still doing a syscall for each of the I/O operations. So doing it inline doesn't save you pretty much anything there. So most of the benefits that come from IOU ring are kind of mitigated for the ring buffer if you want to make it work on like Mac or Windows. So instead of a ring buffer, you can use an intrusive linked list of operations. So this way, the user provides the memory and what to do with the result. And so you can decide how to store that, how to efficiently batch schedule it, whatever works for Mac and Windows for your system. And so this system is actually used in Tiger Beetle right now. I actually started a year ago working on porting Tiger Beetle, because back at the time, it only supported Linux IOU ring. And so I was tasked with working to support other systems like Mac and Windows. So I ported Tiger Beetle to Mac OS using the linked list version. And then we just went all the way and imported it to Windows. And so now we just have a cross-platform IOU ring implementation in Tiger Beetle just sitting there. And we use that for efficient disk I/O dispatch. And so Jared made a pretty smart decision and just took the code, copied it, and put it into Bun. But he made the weird decision that he copied everything except the Windows portion, so Bun still doesn't support Windows for whatever reason, which it can, but I don't know why he did it. But yeah, these are just the two libraries that I know of that are written in Zig that are also use the cross-platform IRUing. So we have a bunch of stuff that are already using it in practice, so it seems like a good idea to put it into a standard library at this point. So should we just plop it in there? That's kind of a hard question because we still have the Zig event loop. So the Zig event loop is basically our reconciliation of how to do asynchronous I/O. The model is pretty much copied from existing systems like Golang or Tokyo, where you have multiple threads and there's a runtime in the background that handles I/O that dispatches your threads like a thread pool and does non-blocking I/O at the same time. And so that kind of doesn't fit well with the IRUing approach because IRUing is one ring buffer in, one ring buffer out. That one ring buffer in is not synchronized. So this doesn't work with multi-threaded. If you want to make it multi-threaded, you probably just wrap it around a mutex, but that doesn't scale and that kind of defeats the purpose of having a event loop that's also a thread pool. You could also just use a IRUing per thread. And so that's normally referred to as thread per core architecture. This is actually pretty popular. There's some blog posts from Red Panda, which is a database that does it. There's some gist I have that just benchmarks this approach versus the event loop, and this actually is pretty efficient. It's efficient because there's pretty much no scheduling overhead. So in a thread pool, all the threads normally have to race to each other to grab the same task or try to grab a different task, but it's all on the same resource that they're contending on. In a thread per core architecture, everything just has its own queue. There's no synchronization overhead. And so this results in like the highest throughput you can get, higher than Golang, higher than Rust, or any other form of like custom architecture for I/O. This is also what's used by Nginx. You may probably know that from being dominated by pretty much every web server on the web right now. H2O is also another web server. It's less popular, but it's like really specialized for high I/O throughput. There's also LA proxy. That uses as well. It's just a TCP server for Linux that's just like Nginx, but for like large proxies. The issues with these is that they're generally paired with like Linux specific APIs. So like Nginx or H2O, they will have systems where they can restart the server by binding the port that the server uses to like multiple sockets and then like transition it that way. But not all OSs have that, and to support that in a thread per core architecture wouldn't make sense for the standard libraries or event loop. So should we just get rid of the event loop? Because IRUing seems to be the future of I/O. Like it solves all the batching issues. It solves the multiple syscall issues. Jens is working on it, and he's pretty much optimizing it every day. He's getting the latest hardware to make it as fast as possible. So with the current event loop being a thread pool, it doesn't map as efficiently to IRUing. So one of the questions is, should we just dump it? Before we do that, let's just see the programming iceberg of event loops, because that exists. So at the top, you have single-threaded languages. This is where everyone is just coasting. You're single-threaded. You can use whatever system you want for I/O. IRUing works. You don't have to worry. We're not those. The next system is actor systems. So these ones, they can use non-blocking I/O, but they're also multi-threaded. So IRUing is also off the table in some capacity. They also do not like to share memory, at least in the programming model. And we're not that too because we have shared memory. And so the next part of the iceberg is ones that have shared memory, ones that are also thread pools, and ones that do non-blocking I/O. And this is basically just the Rust ecosystem and the Golang ecosystem. There's probably others, but these are the most famous. Tokyo's runtime is actually just a port of Golang's runtime, just with their own specific stuff. They use all the same scheduling constants and all that. And then the last part of the iceberg is probably something most people won't touch. It's DPDK, which is like custom driver for doing I/O on Linux. And it's also the C-star framework. So C-star is a thread per core architecture that is used by SkylaDB. And it's a database that's like tuned. If you could write the most efficient database in the world, that's probably what SkylaDB would be. Because it takes over the entire system. It assumes it knows the architecture, it's Linux only, and it tries to do everything it can to be fast. It implements its own TCP stack, and then implements its own driver and I/O interactions. Like this is the lowest level of the iceberg that you'd probably reach to besides like custom FPGAs or whatever. But we're not that either. Zig's current event loop is in the Rust and Go section. But what if we could do something that's in the middle? Something that's closer to C-star, but not exactly the multi-threaded approach that we had before. So one idea is to still have the cross-platform I/O earring, but then also have a thread pool on the side. So basically, the users are more explicit with scheduling. So the user would be the one to decide if they want to do a thread per core approach, if they want to do I/O earring plus thread pool, if they want to not even have the thread pool and not have the thread overhead cost and stuff like that. We also would not have a global runtime because, again, the user decides what runs on where. So we can finally remove I/O mode that I'd like to remove because it causes so much confusion with your blog post on colors async. We could also remove the standard libraries event loop. So let's try to actually apply this to existing projects. Like one of them is obviously the HTTP server. So an HTTP server doesn't really care about CPU throughput. It's more so about serving requests, each request in the smallest amount of time possible. So it's very latency sensitive. So in that case, you'd probably use multiple earrings because they have the lowest overhead for scheduling and they have the highest I/O throughput. Let's say you want to do distributed computing. This is generally what people do if they have specialized workloads. So Lithu actually wrote a blockchain and it uses something similar to this. It has one I/O thread and then multiple CPU threads for doing all the hashing. So this is generally the approach that people use to substitute for the event loop. So the good thing about this is that if you have CPU bound work, the thread pool can handle that. And then the I/O part will handle all the efficient I/O, even if you're not I/O bound. But what if so we cover the cases of I/O bound, which is HTTP server, CPU bound, which is the distributed compute. And if you're not CPU or not I/O bound, then you can just use a single I/O earring. So this is probably what other people that do not care about performance will write, or people that are just looking to write like simple scripts that do I/O, that don't want all the other scheduling issues or scheduling decisions to make. And that's pretty much it for my talk. I was going to make this talk about Zig async, but I decided to put that into a separate blog post because that's a lot to cover, and it's very hard to convince people that it's right because people have different goals on what async is supposed to do. But if you want to learn more about the discussion for getting rid of the event loop, which is kind of the current goal, or if you want to argue for keeping it, you can go to the discussion on that GitHub issue, which I've been pushing for a few months, and also been neglecting for a few months. But for existing implementations of this, you can go to Tigerbeetle's source code. Lithu's Lithu's repo also has the thread pool implementation if you want to just copy that. Bun also copied my thread pool and then used that, and then he had issues, but then he modified it, so it's fine. And yeah, that's it.
King. Okay. Questions? Any questions? Have some time. I see one hand, maybe two hands. Okay. Coming to you.
Hey, thanks. Great talk.
Thanks.
So I was wondering if you've seen anything around, looked into the research around something called LMAX disruptor, which was sort of an approach to concurrency that, well, it started in the financial application space, and the idea was to like avoid locks and system calls altogether to hit the hardware caches when you're doing concurrency more. Like, it sounds like maybe that's what U-Ring would get you to a little bit, since you have fewer syscalls. But yeah, any thoughts on that?
I played around with LMAX. Its idea is to have queues for multiple subsystems. It's similar to the idea of libdispatch or Apple GCD. It's their own framework for doing scheduling in a way that's actually benefit Mac OS's user space specific domain. But the idea of having queues is actually pretty efficient. It's just most people don't think of concurrency that way. So it's hard to put in like a standard library or put in somewhere where people will reach for a tool that they probably exists in other languages but doesn't exist here. LMAX distributors queue in particular isn't, it's going to be controversial, but there's parts of it that aren't that efficient that scale even though it's highly optimized. I found this out through some of the benchmarks, specifically the npmc queues. Those can be optimized in, by using, what was the name? Vukov's npmc queue. I think it's used in Rust Tokyo. It's also used for Erlang's message queues. But LMAX's idea of using queues for things is pretty efficient. It's just, I wouldn't say to use its specific implementation for it.
Okay. Next question.
So is IOU Ring a user space implementation on Windows?
No. IOU Ring is a way for the user and the kernel to send syscalls to each other with a minimal amount of syscalls. So
how do you do that on Windows though?
So Windows 11 has its own port of IOU Ring coming, but one, I don't use Windows 11. Two, it only supports file reading, so it's very simplistic right now. The only system that has something like IOU Ring supported by the kernel without having external drivers is just Linux. So to make it,
just emulate it in Tiger Beetle when you're on
yeah, we basically just make a API similar to IOU Ring using the queues, but underneath for like Mac it uses KQ. Underneath for Windows it still uses IOCP. So it's not as efficient as it could be.
Any other question? If I don't see your hand, start with them. I mean, okay. I think that's it then. So, oh, I know. There's a question. Okay.
So we didn't see the sweetest thing. You said you did the HTTP server, right? So where are the numbers?
See, one thing I've started to do, especially with my posts online, is I avoid showing benchmark numbers because people always derive the wrong conclusions from them. Specifically with the HTTP server, I didn't want to show how fast it could be. I had an idea to show it, but then I was too lazy to put it in, and I didn't think it would be convincing. So instead, I just talked about how to achieve it rather than what it looks like in practice. I don't know if that answers your question.
Okay, then thank you very much. Give it up for Kate.